I won't use the mic. I think you can hear me over at the back. Okay. It is really my first time in an art gallery in this capacity. I'm a scientist and I work on the question of what are the fundamental laws of nature. And this is, depending how you look at it, it's a glamorous profession or it's not. It's really something quite, it's connected with mathematics and it's connected with experiments, and I won't be able to describe any of that here. But on another occasion, I'm happy to describe that too. It's not all that difficult. But here I was told that this project in this gallery is on the nature of time, and the artists are sort of exploring what time means. And what I think might help or it might hinder, I'm really not sure, would be for me to tell you how a scientist thinks about time. So I'll do that in a presentation that should take about half an hour or 40 minutes, but it can take longer if you interrupt, which I'll be very happy for. And probably what I'll try to drive at is, what do we understand? And I'll only briefly mention a few things that we don't understand. But for the most part, I'll try to tell you what are the surprising, interesting things that we understand and that perhaps we didn't understand more than 100 years ago. So we've only started understanding essentially in the 20th century. And so let me just start without any further ado. So I hope you can see this clearly. Is it focused? All right. I think maybe just a little focus. Picture of what's his name, and an illustration of the effect of gravity on space and time. Just an illustration. On the right side, you have something that all of you probably have seen and hated in school, which is gases in a container expanding and so on, pressure, temperature, volume. And these will anchor the discussion in a way that will become clear as we go along. So I always find it useful to start with some quotations because pretty much anyone who's said anything has said something about time. And so I picked a few that illustrate different things, and I'll just start with the oldest one I have, the Roman poet Ovid, who actually said tempus fugit, time flies. It's quite remarkable that 2000 years ago they had the same feeling that we in this modern computerized internet age have, without their mobile phones ringing all the time. And here's Einstein, who said, "I never think of the future, it comes soon enough." And what I want to stress about these two, one by a poet, one by a scientist, is both are talking not about time, but about how we feel about time. It's quite different. Now, here's one more, which everyone likes. How long a minute is depends on which side of the bathroom door you're on. And again, you can see, I think, in the most powerful way, how it's about us and not about the minute of time at all. I don't know whose all was, but I think just a generic smart guy who wrote these things. Now, John Wheeler was a very respected physicist, and he said time is what prevents everything from happening at once. Again, he was trying to be funny. And you see, we have 4 quotations, and all of them, some are funny, some are less funny, but all of them are about how we perceive time. Okay? And this gets a little discouraging to the scientist because we have a completely different notion, and it's a British poet who put this very well. He said, "Time goes, you say, no. Alas, time stays, we go." And this very profound observation by a poet, as I said, provides a link to the way I as a scientist think about time. Time is there. It doesn't depend on how we experience it or perceive it. In fact, talking about our perception of time from my point of view is distracting attention from time itself. It's time we want to understand, and not our perception of it. But you as artists might want to do the opposite. You're completely free. It's a democracy. If you want to understand how people feel about time, that's a valid project too. But that's not our project. I just wanted to emphasize. Our project is what is time, and to the best extent possible, what is it even if we weren't in the picture? That's sort of the question. Another way of putting it is that time is unrelated to life. And I've illustrated this with these two pictures. You see they can be about the same subject, but one is time, and you see from a scientist's point of view, beautiful, colorful. Life, on the other hand, we sort of tend to look down on it, drab, black and white, not interesting. I'm exaggerating, but this is just somehow to anchor the discussion. So let me then, with that prelude, get to the question, what is the nature of time as we understand it? Now here I want to emphasize the difference between teaching something and telling you something. When we teach, we start from some premise which everybody accepts, and then we go through steps and we come to a conclusion. Then people understand or don't understand. Here I cannot do that, and so I'll be telling you things, and therefore there isn't an issue of whether it's being understood or not. It's not being explained, so you needn't worry if it's not understood. You just hear some words, and if they strike you as interesting, please go home and sort of look up sources and think about it. If not, that's also fine. But anyway, I won't be using anything very technical, though there'll be one equation in the whole talk, and it will come fairly soon. So one thing Einstein taught us, which we hadn't realized before, and which in particular Newton and Galileo had different views on, was that time is in some ways similar to space. It's a dimension. Space is a dimension. So this is a direction or a dimension. In physics we would call it x. X is 0 where I'm sitting. If I like, then it's 1, 2, 3 in some units. That way it's -1, -2, -3. It goes from minus to plus infinity. If that's x, I can call this one y. I can call that one z. And with that I've exhausted space. There are only 3 independent directions. But there's one more, says Einstein, and that's time. And the funny thing about time is that we're not even quite sure that it goes from minus infinity to plus infinity. It actually goes from the beginning of the universe till wherever it goes, which we can only speculate about. Maybe the end of the universe, or maybe forever. It has different characteristics from space. What Einstein understood was that if one person is in a particular frame of reference and another one is in a frame of reference that's moving past, then the person who's moving gets space and time mixed up. Okay? This is his theory of relativity, not in equations, just in words. And it's a little bit similar, this analogy may help you, it's a little bit similar to rotation, in which we mix up 2 space directions. So let's see what I mean by that. Here's a map of India. North is up, and there's a little grid that I've drawn on my background page, which has an arrow up and an arrow pointing, so one arrow pointing north, one arrow pointing west. So you could say that my blue arrow that's going up is parallel to the arrow of north in this map. Now let me rotate the map, okay, relative to the arrows that I've painted. And now you see that north is actually going that way. I haven't done anything, I've just changed the map, the position of the map. But now you see that north on the map is partly along north on my blue arrow and partly along east on my blue arrow. It's a little bit of both. It's a combination of the two. It's a direction somewhere in between north and east, right? If you would take that direction on my map that way and put that arrow on my grid, you would say, well, that's sort of northeast in the direction of Assam or something. Are you getting me? Is this clear? But this is just the effect of rotation, so it can't be very, very significant. It's just how I choose my frame of reference. Well, what Einstein understood is something similar, not identical, but very similar happens with time. So if I choose my frame of reference, not rotated, but moving with some velocity, then time and space start to get mixed up. What was only time or only space now becomes some part space and some part time. And so after Einstein, we started calling this whole thing space-time. So that's special relativity in a nutshell. Now, let me show you the one and only equation of this talk. Of course, even before Einstein, we knew that your position changes in response to a moving frame. Give you an example. You sit in an aeroplane, you're strapped into your seat. So in the frame of the aeroplane, you're going nowhere. You're exactly in the same place at the beginning of your trip as you are at the end of your trip in seat number 15C. Okay? However, the frame of reference, having moved with respect to the Earth, you actually end up in a different place with respect to the Earth's frame of reference, not with respect to the plane. And that, of course, was the goal of your trip. Now, in equations, we encode this in these equations, and what these equations say is my position in, let's say, in the Earth's frame, which is x, y, z and t on the right, is related to my position in some other moving frame, that's x prime, y prime, z prime, t prime on the left, by that little shift v times t, where v is the speed at which this moving frame moves and t is the time elapsed. So let me show you a simple calculation based on this equation. If I'm in the plane and my seat 15C is defined by convention to have x prime equals 0. X prime is 0 at all times. Okay? The plane is moving with velocity v. So after a certain span of time t, which could be 8 hours, what's x? X obviously cannot be 0 anymore. At t equals 0, x was 0. After sufficiently many hours, x is equal to v times t, which means the distance I've traveled is the velocity times the time of travel. So this is a familiar equation, and it does say that position is relative to a moving frame. That is, my position in one frame and in a moving frame with respect to that is not the same. Okay. However, if the frame is moving along the x direction, then my y and z positions haven't changed. Let's say I'm in a car moving that way, then my position along this direction or along that direction haven't changed. And notice that my time also hasn't changed, which means my watch is the same, functioning the same way as the watch of a person in the other frame. Okay. Now Einstein had a more complicated equation, which is full of square roots and pretty scary. But if you look at it carefully, you'll see it's not so weird at all. First of all, it has a new number in it. Not just the velocity, but also a particular velocity c, that's called the velocity of light. Okay? You'll notice that there are some complicated expressions which involve v upon c. Okay, v squared upon c squared, or v upon c, the whole thing squared. Now, let's say v is the speed of an aeroplane, that's about quarter of a kilometer per second. The speed of light is 300,000 kilometers per second. Okay, the ratio of these is incredibly small. For such frames, you can forget about v by c. V by c is 0. You can put it to 0. Now, can you put it to 0 for me in that formula on the right? Square root of 1 minus something, but that thing is 0. So it's just square root of 1, that's just 1. So that whole complicated factor in front is gone. Now can you see that x prime on the right side and on the left side have become the same? If you forget about the factor in front, x minus vt is the same. Not only that, if you go down to the last equation, you'll see that this square root factor drops out for small velocities, but also that extra factor on the right, vx by c squared. That's also very small when v over c is small. So that also can be dropped and we get v prime equals t. So now you understand what Einstein did. What he did was to say, nothing's wrong with your intuitive thinking based on the left side, which we call Galilean relativity, but it will be a mess if you try to extend it or extrapolate it to velocities close to the velocity of light. Velocities which, by the way, we never reach whatever we do ourselves, but there are objects that go that fast. Light, for example, itself goes at the velocity of light. So if you use the equations on the left for aeroplanes, you'll be fine. You can use the one on the right, but it's the same. If you use the one on the left for things, little things that travel at 200,000 kilometers per second, you'll get wrong answers and your experiments will not agree with these equations. They'll agree with those equations. Now see, the fundamental difference in the two equations is that t prime is not equal to t. Time in a moving frame is not the same as time in a fixed frame. That's a key result of relativity which departs from conventional wisdom before Einstein. And in fact, experiments have proved quite conclusively that he is right. Now for those of you who are a little comfortable with mathematics, notice that when v by c becomes as large as it can, remember that velocities are all less than the velocity of light. That's one thing he discovered. So if v by c is very close to 1, then 1 minus v squared by c squared is a very small number. 1 over a very small number is a very large number. So we see that this formula causes a stretching of space from the first line and a stretching of time from the last line. Both of them get stretched. These are the phenomena that we are familiar, that we've heard about. One of them, the last one, is called time dilation. It's the statement that time appears to slow down when you view events from a reference frame that's moving very fast with respect to the event. Okay? This is why Einstein made time relative. He said even the seconds which elapse in your watch will not be the seconds that elapse in the watch of another person moving past me at velocity v and watching me. Okay? So here in a nutshell is what we learned 106 years ago in the year 1905 when, not completely out of his head, but after a series of experiments and many other works by other scientists, Einstein sort of announced his complete theory in one long paper. Okay, the theory of special theory of relativity, and it had these two features. One, that you see that time and space get mixed up. You see that both my formulae there have both x and t in them. This is the statement that they get mixed up and that they also get stretched. People weren't so worried about space. They said space, space can change, but time, Newton had said it's eternal, immutable, it flows in and of itself. Well, Einstein said, too bad. That doesn't give correct results consistent with experiment, and this does. This is the reason we believe this formula. So this is one part of what I wanted to say, and let me just say this again. Relative to a moving frame, time appears to slow down. Einstein's discovery, but it would be a mistake to think that the person who is moving thinks time is slowing down. It would not be the person who's in the moving frame who would see their watch ticking slowly, because you're in the same frame as yourself by definition. It has to be a person in a different reference frame whizzing past you and timing what events are happening in your watch. They will see time moving at a different rate. And the funniest part, and this is totally bizarre but one gets used to it, what they see about your time slowing down, you will see about their time slowing down as well. Because if they are moving with respect to you with a velocity v, so are you moving with respect to them. The velocity v is just the difference between your two velocities. So if they are moving that way, you are moving this way, but the speed is the same. So that's quite amazing. So you would think that when they see your time slowing down, it means you're seeing the time speeding up, but that's not how it happens. Each person sees the other one's time slowing down. You would think at this point they could stop and compare notes and find a contradiction, but if they stop, then the phenomenon goes away. Because the phenomenon happens only as long as they are moving at velocity v, where v is a few 100,000 kilometers a second. So you never notice any contradiction. Okay? But this experiment has been done not with people, but with little objects, particles, and every time it returns this result, which I've just told you, that time slows down. Where is it relevant? Well, if you look up at the ceiling, you will not see them, but there are cosmic rays going through this room right now, even as I speak. Okay? These are little particles with names like Greek letters, like you see over there. Some of them were created outside this galaxy, some of them were created above our atmosphere. Whatever they are particles that scatter, that decay, that travel. But one of them that's very interesting, it's labeled by the symbol mu. I don't know if you recognize the Greek mu. It's a grey line somewhere in the middle. On the left, that muon would have no business reaching the Earth, because in the time it takes to reach the Earth from the upper atmosphere, it should have decayed into an electron as shown in the figure. But it doesn't, it reaches us. Mystery. Okay? We love mysteries in science. Why does a muon reach us when a terrestrial muon, if I put it on my table, it's poof, it's gone in a few seconds, but it lives the 10 minutes it takes to reach us from the upper atmosphere? The reason is time dilation. Okay? In its own frame, it's only lived 1 second, but in our frame, it's lived 10 minutes long enough to reach us. So these effects are not hypothetical, they're not so subtle that they can never be seen. They can only not be experienced by human beings directly, but they are experienced by objects and we can measure them. So that is one part of my talk, and I think I'd like to pause now and let's see what you have to say or ask. You'll have to say something, otherwise I won't go on.
I don't believe that time is the fourth dimension because it's completely different from the others. The other three dimensions can be exchanged.
You're right.
So how? It's a completely different entity.
Yeah. It's a very weird thing. Let me give you an explanation which involves a tiny bit of maths, and you will see that both what you say and what I say can be true. Supposing I have a triangle in which one side is x and one is y. It's a right angle triangle. Pythagoras theorem says that this side is given by x squared plus y squared, and the square of this side. Now in the geometry that Einstein teaches us, he says take this to be a space dimension and this to be a time dimension. Then he says the diagonal will not be x squared plus t squared but x squared minus t squared. Time enters the formulae, the same formula as space, but with a relative minus sign. Minus sign makes all the difference. It means you cannot exchange space with time. But if you keep x squared minus t squared fixed, you can change x, you can change t, but x squared minus t squared, that amount remains fixed, and that's what happens when you travel in a moving film. So, in other words, time and space get mixed up, but the intrinsic nature that time is, we refer to time as time-like. Time-like is a particular mathematical property. A time-like object cannot be exchanged with a space-like object. And here's an example. Here's a time-like, so here are two examples which typify how time alone and space alone work. One is time. I'm here in this position, and 5 minutes later I'm still here in this position. So two events, they're separated only in time because I haven't gone anywhere. A different event is that I'm here at this time and he's there at the same time. These events are separated in space but at the same time. Relativity forbids you to exchange these two kind of things, and you can see that if you could exchange them, you would go crazy, because two people sitting in different places at the same time could be transformed into two people sitting at the same place at different times. It doesn't happen. And this is the root of the fact that you see time differently from space. Nevertheless, we can mix time and space. Both are true. It's strange and it will get stranger. Time has features that are different from space, but it has features that are similar to space. Both. But I do emphasize it's not the result of anyone's imagination. All these facts were drawn from experiments on these kind of elementary particles. So whatever facts are deduced from that, we sort of cannot take them or leave them. We only take them. If you didn't take them, your mobile phones wouldn't work. Just to give you an example. They depend on these kind of formulas. Any more? Please feel free. I think everybody's wondering whether they have a smart question. Don't ask a smart question. Just make a comment or ask a question. Am I intimidating these people? I can go.
I think, yeah.
Okay.
Let's go on.
Let's see what happens.
Yeah.
Yes, please.
So, there's a film called Inception. Have you watched it?
A film called Inception? No, I haven't.
No, it deals with time when someone's put to sleep or someone's dreaming.
Okay.
So, how is dream time relative to the concept of time? What's the connection? Is there a connection?
So the connection, I think I made clear right in the opening. That has to do with our human beings' perception of time.
Okay.
It has nothing to do with time itself. And a very easy way to show that is that when you're dreaming, I might not be dreaming. Okay. If time were to actually stop, then I would find myself frozen during the time that you're dreaming. Okay. But instead, everybody experiences time independent of everybody else, just as they feel like. You might be feeling uncomfortable and wishing time would go faster. Somebody else might be enjoying themselves and wishing time goes slower. Third person might be asleep and not even aware that time is passing. So the moral of that story is these differences don't depend on time at all. They depend only on human beings. And for a physicist, human beings are totally inessential to the problem. We are only essential to the extent that we have to be there to study the problem, but we don't want us to be there in the problem. That just makes everything too confusing. And lest to think this is because we are very heartless and we don't have proper social skills or we don't like other people or any of those. It's not that. We are interested in accurate answers. You see, human beings and more generally living beings are so complicated that you cannot do anything accurate numerically with them. There is nothing you can do accurate numerically at the kind of accuracies we want to understand with living objects, and so we leave that to the biologists. We say, you draw your nice pictures, we are going to calculate numbers which are phenomenally accurate. Numbers to 8 decimal places. You cannot imagine that excitement that you calculate something to 8 decimal places and you measure the same thing to 8 decimal places. Both of these are a challenge. How on earth can you make sure your building hasn't moved by one point in 8 decimal places while you are doing the measurement? You have to compensate for everything. And let me just digress from the theme of my talk. In this famous accelerator at Geneva that you must have heard about, the Hadron Collider, its predecessor, the electron-positron collider, for which the tunnel was built, they found a very strange fluctuation in the electrical measuring instruments, an electrical fluctuation which occurred 4 times a day. And you know what they figured out finally what it was? It was the train running from Geneva to Paris. The high-speed TGV train runs 4 times a day and their instruments were getting little oscillations at exactly the time the train was passing a couple of kilometers from the site. This is whatever the electrical effect of the train going through the ground 2 kilometers away, they were able to measure that. The height of the water in Lake Geneva was also affecting this. This is the kind of precision. And this is why we try to keep people out of it. They're very bad for precision.
I have a question.
Please.
Einstein gave you an example of twins and one of them was scientist. What was that?
Yeah. So it's similar to what I said, except it has the form. So here it is. When a person is moving, they see time moving more slowly from your point of view, or you see time moving more slowly from their point of view. Now, if the person whizzes past, goes a long distance and then turns around and comes back, in both directions you see their time moving more slowly. So by the time they come back, now they're back and they've come to your reference frame, they come to a halt, and you realize that they're actually younger than you are after this trip. Okay? Now, the weird thing is, how can you tell that that person traveled and came back and not that you traveled the other way and came back? And here there's a little trick. In order for the person to come back, they need to stop, turn around and come back. That involves acceleration. And that makes a clear distinction between that person and you. You didn't accelerate, you stayed in one place. That person goes whizzing by, then slows down, comes to a stop, turns back, and speeds up again and comes to you. And in this process, they have actually, nothing in their rocket ship has changed. They and their little pet dog and their flowers and plants all are aging uniformly, their watch is moving uniformly. But by the time they can compare with you, they discover that they are a lot younger than you are. So the total amount of time you have experienced is more. Okay, but there's no sort of tragedy here. Both of you have lived the amount of time that you have lived. Okay, it's just that when you compare two people, then by moving one of them ends up being younger. It doesn't help that person prolong their life. Okay, but it would help that person in a sense to travel into the future, because when they come back here, they'll be living in an earth that's not the one that they left but 100 years or a million years later. But I emphasize, to have any significant effect, you need to travel at speeds which we can't begin to imagine. That's the twin paradox. Thank you. Okay, so let me briefly say what happens in the presence of gravity. So it's bad enough that time and space can rotate into each other. When you have gravity, what it does is to take this continuum of space and time, depicted here as a grid, And any object which has a gravitational force, basically any object with a mass, will curve this thing. And we all know what is curved space. For example, the surface of a ball is curved. Okay, it has its characteristic geometry. If you draw the straightest line you can draw on a surface of a sphere and make a triangle out of such lines, the angles will not add up to 180 degrees. They'll add up to more than 180 degrees. Okay, that's an effect of curvature. Curvature of space is complicated but very understandable. It was understood centuries ago. Curvature of time along with space is quite bizarre. Okay, luckily we can alternatively understand this probably not. This theory is considered hard even for physicists. Special relativity we can teach in college. General relativity we teach people who have already got a master's degree in physics. It takes that long. And it's not something to be proud of or ashamed of, just a fact. It involves a lot of mathematics. So I think this is the best I can say about it, that gravitating objects curve space and time. So one line statement. Now, let me at least show you one little physical effect this can have. You've all heard of black holes. Now, a black hole is an object with such powerful gravity that anything which comes too close to it, inside its horizon as we say, is sucked in inevitably. And this is nicely depicted here by a little boat. And that circle is the so-called horizon. Okay. Now the horizon is not actually it's not exactly a package inside which the black hole resides. The black hole is an object with a gravitational field, and that field is present everywhere, and you experience attraction. As you are attracted to the earth, you are attracted to the black hole. So if you were this boat over here on the right, and if you weren't moving away, you would be drawn towards that, just like to anything else, just like to earth. If you were up in the sky and not in a rocket ship going up, and if there was no air to support you, you would just come plummeting down. That's normal. But the interesting thing is that by the time you come to the horizon, time itself slows down to a point where it almost comes to a stop. Light itself is stationary. How do we think of light being stationary? Well, light tries to travel at the speed of light, but this black hole is pulling it. So in some sense, roughly, you can think that it's sort of stopping light. Since light is the fastest thing there is, not only light but everything is stationary, which means that once you're on that thing, any amount of rocket power you have cannot propel you out. Okay? But the way that works is that time intervals get stretched, exactly as I showed you earlier. Due to a moving frame, time intervals can be stretched. Here, due to gravity, time intervals are stretched. We say there is infinite redshift at the surface of a black hole, and therefore the way time ticks for that boat sitting there, as viewed by somebody standing far away from the black hole and watching, would be very, very slow. Okay? And that's sort of one consequence, a very extreme consequence of the curvature of space-time by gravitating. Black holes we like because they are the most extreme gravitating objects, but the Earth also curves space-time. It's just a very small effect and it's almost negligible. Okay.
Sorry, just a question. Could you put the last picture?
This one?
Yeah, you say light is stationary on the event horizon.
Yes.
So if light would be just inside,
yes,
the event horizon, it would be pulled in.
Yeah, I'll tell you what happens, and I didn't say it, but now I'll tell you. Once you're inside, just inside that, time and space get exchanged. Okay? So what was experienced as time relative to the person outside, inside is experienced as space, and that has the effect of blocking completely the view of inside from outside.
It's not that inside the event horizon the force of the pulling to the light is faster than the speed of light.
Yeah, it's not actually, because that would violate the statement that everything should be slow.
It just inverses.
It inverts space and time, and in a peculiar way it does pull you in, but just as an example, you wouldn't experience a catastrophic force if you were just inside that line. You would, from outside to on the line to inside, you in the spaceship would be floating around blissfully, and you would never realize that you had passed the point of no return. Okay? The place where life becomes awful is down there, where the mass of the black hole is concentrated, and there you will be crunched by a force of gravity, but not at the horizon. And people love this because it means the horizon is a point where the nature of the world changes, but the change is not evident to you, the person traveling. The change is evident to a person who is at rest outside. Okay? And they know that they have lost you forever. Let's say you are sending little SMS messages every second. They start getting your messages more and more slowly, and when you cross the horizon, they never get another message from you. Quite beautiful actually. Tragic. Okay, now this was stuff we know, so let me briefly mention stuff we don't know. Very briefly, because actually we don't know it. Now all this was how we think of time in a world which is not quantum. The weird thing about the 20th century is we had to not only adjust to relativity, we also had to adjust to a new phenomenon called quantum theory, which has to do with the discrete nature of things. And ultimately, quantum theory tells you that whatever you think would be continuous is actually quantized, discrete, little packets. Okay? Now, if you incorporate quantum physics into the study of gravity, which curves space-time, then you need to have, first of all, a new theory. This is the theory on which I've been working for the last 25 years. And let me just say a couple of words about this theory. So it's based on the idea that your little electron, which you see as a little point-like particle, at very, very tiny scales, much tinier than what we can actually access, resolves itself into a little loopy kind of object. And this has the effect of giving us a consistent theory in which quantum physics can be incorporated along with gravity. Otherwise, it's not so easy to have such a consistent theory. But this is not my main point. You don't need to know anything about string theory for what I'm saying. But what we learn from this is that space is probably not smooth and fundamental at the underlying level. Rather, it's an effective description. And it's quite easy to understand what an effective description is, because look at a glass of water. Okay? You think water is also smooth. When you paint it with a sweep of the brush. Okay? Because it's smooth. It doesn't have little dots in it. But of course it has little dots. It's nothing but a bunch of H2O molecules, each of which is a little dot. Okay? It's only because your eyes don't have the resolving power of a microscope that you see it as smooth. If you went too close, you would see it as grainy. When you back off, you see it as smooth. But this theory says space is like that. Space we see as smooth. When we move, we don't just hop from one point to another point. But at very, very tiny scales, it seems space might be grainy. And I've tried to depict a grainy space over there. So each of these little circles is one grain of space, and they mesh together to form all of space. It won't kill us to believe this, because how do we know? We don't see space at that kind of tiny size scale, and space really means empty space. We are never in empty space, we never see it, we never experience it, and these things are very, very tiny, much, much smaller than atoms or electrons or anything. However, Einstein, as usual, causes the problem. He says space and time are part of the same fabric, so if space is effective, time should also be effective. Now we don't understand what this means. What on earth does it mean that time is an effective description of something? What is the thing? In physics, we don't know how to write a formula unless that formula tells us the time evolution of something. Even in quantum theory, it tells us the time evolution of the hydrogen atom. Okay? But if there is no time, then there is no evolution, and there is no anything, and then we are kind of lost. We have some ideas, but we really don't know what. So this is kind of at the frontier of trying to understand space-time. Space being emergent, okay, but time being emergent and effective, very, very strange. We have our thoughts, but it's a very, very big puzzle. Okay, good. So that's half of my talk. The other half which I'll give or not give as you people prefer, is on the arrow of time, and it basically deals with the question, why does time appear to have a direction? There's another problem with time compared to space. Space, alright, it has a direction. He is plus 3 units from me, but that place is minus 3 units from me. So I can go plus or I can go minus in space. It doesn't bother me either way. It's in fact a pure convention. But in time, it's not a pure convention. You know, what's happening tomorrow and what's happening yesterday are not just related by change of point of view. They're really different. At least for us, they're really different. Maybe not for you, I don't know. For me, it's really different. So, why is that? That's called the arrow of time. The fact that time appears to move forward to everybody. So, if you want to discuss what I've said before this, we can break for a few minutes and then we'll get on with the arrow of time. Is it possible to show? No. And in fact, it's also not possible to show that space is effective. We could show that if we really had a theory in which space is made up of dots, and we say that really these are the dots and these are the observations, but at long distances where we can't resolve those dots, we see a continuous space. We don't know that for sure.
So the dots are supposed to be what?
The dots are supposed to be the ultimate granules of space. That is to say, space itself, the fabric of space, which we think we understand. We understand mathematically. Physically, we don't, perhaps, I don't know, it's just the sum total of our experiences. But, you know, how well do we know what it's like at very short distances? People talk about a foam. It's a bubbly thing. You know, actually, quantum mechanics does say that empty space is a bubbly thing, but it says it's bubbly because things like electrons and positrons and photons all sort of pop out of nothing and pop back into nothing. It's like a sea, a calm sea on which ripples just happen on their own. They're called quantum fluctuations. Now the extra statement is that space itself has quantum fluctuations. Well, you know, one should not try to connect it with one's personal experience. One should try to analyze and see if one can detect this thing. But at present, we have no idea how to either detect or to model in a theory that space is granular. But I think people are quite sure it must be. There are many reasons in the theory, in the structure of the theory, to believe space is effective, emergent. Maybe when the universe was formed, the concept of space wasn't there. That evolved eventually. It's a low energy view of things.
And what are the reasons?
Yeah.
For example?
Good. Okay. Quantum theory says that there's a probability for everything to happen. That things are not completely determined, they are probabilistic. So, supposing I say that my space-time here and now is approximately flat. Quantum theory says, yeah, that's true for gross observations, but if you would be very accurate, this space-time should be fluctuating. Everything fluctuates. You and I fluctuate, the room fluctuates, molecules fluctuate, but even space-time should be fluctuating. Now, if it's fluctuating, then it's not just one thing as Einstein thought it was. Okay, it's not that the field around the earth is one smooth field of force which we experience when we jump out of a window and fall smoothly down. We experience a continuous field of force, but if it's fluctuating, then somewhere in the details it's variable. This force is not fixed. That's the best I can say. You know, so it's not what it seems. Now, a fluctuating thing may be made up of grains or it may not be. Can't say. How would we guess that a liquid was made up of atoms or molecules? Whoever guessed that? Certainly not in the Vedic period, not in the Indus Valley civilization, not the ancient Greeks. It took a while. I mean, people thought of it as a possibility, but until people could actually train their microscopes, in fact, you may have heard of Brownian motion. That's only 100 and odd years old, 120 or so years old. That's when people were sure that things are made of molecules. At the moment, it's only an idea. Okay, so this part I think will be less abstract and I think you'll enjoy it. Unlike space, time only moves forward as far as we know. And so the British astronomer Eddington coined the phrase the arrow of time. And we do experience it. We are all moving forward in time. This is Eddington and that's my representation of his arrow. So the mystery is, why is there an arrow of time? Now here is a literary work which beautifully recognized the arrow of time. The Rubaiyat of Omar Khayyam said, the moving finger writes and having writ, moves on, nor all thy piety nor wit shall lure it back to cancel half a line, nor all thy tears wash out a word of it. What he is saying, if I understand it correctly, is that there is no going back, only going forward. The moving finger is the arrow of time. Exactly the same thing. And it's beautifully represented in this verse. And it's, as you know, this poem is a collection of sad, or at least, if not sad, thoughtful, melancholy reflections on the nature of life, and the feeling that life sort of things seem to keep going on, and you experience as an observer, and you pass your small time on earth and you go away, and so on. Anyway, so this is what how they put it, but it's very puzzling. If time is a dimension, why on earth does it go only forward? And here's a particular puzzle. We know the equations that govern, for example, motion under gravity or motion under electromagnetic force. These equations are completely symmetric under the inversion of time. Just send t to minus t, so instead of flowing forward, it flows backward. The equations are the same, the behavior is the same. So what's the big deal? Very surprising. It's a puzzle. I want to try and explain this puzzle to you. Now here's an example where there isn't a puzzle. Imagine you saw a movie of planets going around the sun. 9 planets all going in elliptical orbits. And somebody just accidentally reversed the movie. Planets still going around the sun. Would you have any difficulty believing one movie or the other? You don't even know which side you're looking at the planet from. Right? How can you say the earth goes clockwise or counterclockwise if you look from this side or that side? So you cannot actually tell which movie is correct and which movie is reversed. So that means that some events in life don't care about this arrow of time, and yet there are others which do. All movies certainly don't look the same backwards and forwards. So I'm going to show you 2 movies, both in reverse. In fact, both are segments from the same movie. And they were made by a bunch of school kids, high school kids in the US, trying to do a project on time. And they were like, let's try to do various things that school kids do, film them. Now it's very easy, people can do it here too, you can do it yourselves. Put that on a computer and play it backwards, and let's make a movie which brings out over several minutes the absurdity or whatever of time going backwards and highlights the irreversible nature of time. But these kids had different ideas, and I think the movie is a collage of different kids' ideas. Some of them are very striking. The first one, which I'll show you, is an event which is absolutely absurd when you view it because it's time reversed. You'll recognize immediately why it can't happen. But the second one, I think the kid who made it thought it was an illustration of irreversibility, but to me it illustrates reversibility. It looks actually quite okay. So 2 movies, each of half a minute or few seconds, but one looks absurd, the other looks okay, both made by the same kids in the same school and both backwards. So let's see them and then let's talk about it. So here's the first one. Was that clear? A piece of paper set on fire, burnt to ashes, and then played backwards. Let's play it again. Starts with the ashes. It seems to be burning, but this is actually the opposite, and the paper is forming out of the ashes. Ashes are turning back into paper. And they've called the paper rewind to show that, prove their point. They are smart kids. This is a very nice little video. It says everything. This is as absurd as it can get. You cannot do this in your house or in your lab. And our question is why. Now let's see the second video that the kids made. Let's watch it a couple of times. That's it. You see a kid running, he turns around and jumps backwards up onto a wall. But isn't that strange? I think I could do it with enough practice. Let's see it again. The funny thing is, he thinks he's proved a point, but he hasn't proved a point. It's actually a reversible event that we've just seen. Okay? As much as planets going around the sun is reversible. So you see, not everything looks irreversible, but some things look very irreversible. So let's go on and try to press home with this point.
Sorry.
And yes, please.
I don't know, it's just thermodynamics, but the process of entropy, how
Yes.
do you see that in relation to time?
Yes, that's what I'm doing.
Oh, well, then
that's exactly that.
shutting up.
Yeah, no, but it's exactly that. Okay. The most irreversible processes are the ones that involve an object with a lot of order turning into an object with disorder. Okay? The piece of paper was ordered. The piece of paper was a single white sheet of paper. It was made in a process which stacked all the paper molecules nicely and sliced them into an orderly thing. All of it looks the same and it's one coherent whole. You can pick it up, you can take it home. At the end, it's basically a bunch of ashes. They might be sitting where the paper was, but if you just puff a little on them, they'll just fly away. So an ordered object has turned into a disordered one. In the second example, there was a boy at the start of it, there's a boy at the end of it. The same boy hasn't turned into a million fragments, thankfully, and therefore there's nothing particular in that experiment which makes it irreversible. So that's the key. So let's pursue that key. Smash a plate, you get a million fragments. Here's another example taken from physics class, which is the same but it looks a little more abstract. Take gas in a small container. So the gas molecules have a freedom to move only in a tiny container. That's the top left one. Now expand the space that the gas can occupy. So the gas molecules expand. So they have much more freedom. So they are more disordered. They can go to more places than they were allowed to go before. And now it turns out it's not possible to reverse that to this. If you bring the pressure of the right thing back to the pressure on the left, you'll find that the temperature and volume are not the same. It's an example of an irreversible process in thermodynamics. Okay? That's a little abstract, but smashing a plate, I think we can all sort of imagine, and in fact, it was beautifully. Okay, so before I give you an illustration, let's think about reversing the process of smashing a plate. Could we reverse it in principle? Now the answer is yes, we could reverse it in principle. All we need is a million plate fragments and a device which will give all of them exactly the right velocity and direction so that they'll all spring up from the ground in a coherent way and come together to form a plate. The problem is that the fragments would like to go into other fragments. There are billions of configurations that those fragments can go into, and only one of those is a plate. All the others are just other fragments. If you smash many fragments together at random, mostly they'll just give you other fragments. But if you smash them not at random, if you select how they smash, they will actually combine into a plate. Conversely, starting with the plate, it can go into millions of fragments in millions of ways. When we smash a plate, we don't analyze that did it go into this or that smashed configuration, because there are so many available. That's quantifying our idea that the ordered object has gone to the disordered object. So going backward is possible, it's just highly, highly improbable. That's the point. And the point is that when probabilities are so astronomically tiny, it's as good as that this never happens. You could set up a set of conditions in which a pile of ash turns into a sheet of paper, but for this, a million people would have to work for a million years, and it just wouldn't, basically, therefore, the same as wouldn't happen. Do you remember this person, Humpty Dumpty? Okay, all the king's horses and all the king's men couldn't put Humpty Dumpty together again. Now you see, he's actually trying to do it, and he's realized that they couldn't do it. The king has everybody in the kingdom under his command, and they're all trying to put these egg fragments back together. But they are not succeeding because it's so incredibly improbable that at the end you will get this egg. By the way, if you break the egg or break a plate into two pieces, you can sort of put it together. And if you could take it to a factory and really, heat up the edges, and you might be able to recreate the plate. So, if it's only two pieces, you can put them together. It's when it's a million pieces, that's when you can't put them together. Okay, so this is the reason for the arrow of time, because there are more disordered systems than ordered ones. Processes evolve in the direction of disorder, and this is the second law of thermodynamics. It just says that. And this is the arrow of time. And this raises a question that might be bothering you. Here's the question. When a hen makes an egg, after all Humpty Dumpty came from somewhere, isn't she creating order? So what is the hen doing to violate the second law of thermodynamics? How did that happen? And the answer is nice. If you look at the total amount of order in the system of the hen and her food and the air around, including the gas she takes in and possibly the gas she gives out if she doesn't have a very good digestive system and everything else, then the whole thing has gone to disorder, but one part of it has become more orderly, namely the egg, which earlier was some molecules running around inside the hen. Well, she did manage to make an egg, and it's great because it's the same reason why we can make this chair, this computer. Every time we make something, we create order, but we pay a net price. The price is disorder somewhere else in the universe. Now, it's not such a colossal price. This is not, by the way, related to global warming or climate change or any other thing. It's very fundamental sense of disorder that we are creating, but we shouldn't worry too much about it. It's not the kind of thing that has a practical implication. So, if we have the resources, we can go on creating order for quite a long time. But it's good to remember that the net result of everything you do is disorder. Okay, in fact, this means that the universe must have begun in an ordered state, because we know it's rolling towards disorder, but there's some order that it can still roll and become more disordered. So it must have started very ordered. So that is how we think about the origin of the universe, the Big Bang or however it started, must have started in an ordered way. But how will it end? In a state that people call heat death. Yes.
I just have one small
Please.
When you spoke about this order and disorder, you spoke about the hen laying the egg and creating order, but in the meantime, so many disorders coming in. Is this where the butterfly effect will fit in or something?
No, the butterfly effect I think has not to do with order and disorder, but to do with causality. The butterfly effect is the statement that a butterfly flapping its wings could have an effect which would have an effect. Each effect can magnify. It's not a question of order, it's a question of what you influence. Okay? Actually, the butterfly effect happens in our lives all the time. For example, I don't want to quote depressing thing, but let's say I call someone over to my house for dinner, they have an accident and they're killed. Okay. Was it something I did? Not really. But now I call them over for dinner. Why? Because somebody introduced me to them. Otherwise I wouldn't have known them. Then I wouldn't have called them for dinner. You trace back, you'll find a whole series of causes which caused this tragedy at the very end. But all of them are completely innocent. What was the person thinking when they introduced me? Not that I'm going to cause some crisis to this person's life. That's the butterfly effect. It's the fact that causality chain of events can lead to a conclusion which could not be imagined when you started the chain of events. This is quite different. This is the fact that everything is rolling towards disorder, and disorder actually is very boring. It doesn't lead to events. In heat death, there are no events. Now heat death, most people would imagine something like that picture taken from Death Valley, but that's not it at all. That's an inaccurate representation. It's not even going to be very hot when the universe reaches heat death. It's going to be actually very cold. Why do we call it heat death? It means all the energy in the universe will have been converted to heat, which is an unusable form of energy. Once it's all heat, we can't convert it to anything. We don't have any. So in some sense, everything would be an undifferentiated mess. and everything would be at some uniform low temperature, and there'd be no motion, no activity, nothing to create the activity. And in this situation, I think one has to say that time will effectively come to an end. Okay? So the universe is heading that way. Should we worry? Not too much, because, okay, before I get to that, here's old Bertie. The whole temple of man's achievement, he said, must inevitably be buried beneath the debris of a universe in ruins. This is his comment on heat death. And you can see how depressed he's looking about it. Why do I say you shouldn't worry? Because heat death will take this many years. And till then, I think we should all have a good time. Thank you very much.
It's like this heat death that you're speaking about, is it like harking back to a period like Ice Age? And
No. Ice Age was very orderly. There were ice caps, they were melting, they were doing things. See, in heat death, nothing is doing anything. Forget life, there's no life.
So life
But even-
slowly disintegrates when you're reaching
Yes,
heat death?
but you have to remember that life arose in the first place. So that means even before life arose on the planet, there was order. So the initial condition when the universe was formed was quite an ordered condition. That's quite amazing. Heat death is a very boring, disordered condition. By the way, it's not the only future. The other future is that the universe collapses back into a crunch. Okay, then the universe itself disappears and there's no question of heat death. But these are alternate scenarios. One scenario is that everything winds down. All are possible.
Can you conclude in your presentation that the Big Bang might be the first disorder in the system?
No, the first order actually, because there was no system before that, and spontaneously it started. In fact, people often wonder whether how could it spontaneously, who was there to start it? But the answer is that there wasn't any universe then. So before that, there isn't even any notion of time. Actually, let me say there was another section I had thought of putting in the talk, but would have got too long. But I wrote about it in a magazine called BBC Knowledge, which comes out, I think it's in one of the recent issues, which is when people ask, so what was there before the Big Bang? And I tried to explain that actually time itself wasn't there. Okay? So the Big Bang is the origin of the universe. There's no question of what was there before. And this origin must have been very ordered. Why, we can still ask, we don't know the answer. But must have been very ordered because there's no source of order. The laws of the universe don't create order. So the only way order could be there is that it was there from the beginning.
So I have a very simple fundamental question then.
Yes.
When you talk about like nothing being there before the Big Bang, no time being there, aren't we calculating time in a sense that which is relative to us? Like since the creation of the universe, since the creation of Earth and to where we are now, aren't we calculating time in reference to that? What if like there is, isn't there a possibility that there may be parallel universes or parallel time systems?
So of course everything is possible, but we can only do what is most consistent with experiments that we see. So we always base our ideas on properties of the universe that we can actually see. That, by the way, includes radiation from close to the beginning of the universe, because that's the radiation that comes to us from the furthest distances away. It's been traveling since the beginning of the universe to reach us at all. And this gives us a picture which I call the ice cream cone picture. This is what I wrote about in BBC Knowledge. So let's hold an ice cream. Let's imagine an ice cream cone. I don't have a drawing. Here's a cone. It has a pointy thing at the bottom. And this arrow along it is time. And we are somewhere here. The universe, as you know, is expanding. And so we are somewhere there. Now imagine we went back in time just as scientists to understand what there was. The universe shrinks. Look at this direction of time. We trace it back and then we reach the point of the cone. Okay? That's where it runs out. There isn't any point on the cone which is before that. It's in the shape of the cone that the earliest point on the cone is the tip. And the cone in our world is sitting inside the world, but in this model, it's the universe itself. There's nothing outside the cone. The cone has everything. So if that picture is correct, then the beginning of the universe is the beginning of time itself. There is no time before that. Can't be defined.
I mean, in a way, it's difficult to imagine negative space. If the universe would be this ice cream cone, which comes down to this point, what would be the negative space of where this?
Where the cone is placed.
Yeah. I mean,
Oh, you mean the complementary space?
yeah. What happens around it?
Yeah, there's nothing else. So here is the point. Imagine you're an ant living on a football. Now, the ant has no consciousness that there is anything outside it. The whole world for the ant is the football. So, we are trying to make a model of the whole world. Okay. So, if you were the ant, you could actually make a theory in which the whole universe would only be that ball, and there wouldn't be any extra dimension which can lift you off the ball. We are in that situation. Now, you could ask that, like the ant, is it that we poor human beings are so ignorant, but there's really some master being watching us from another dimension? That we can't rule out. And the ant also couldn't rule it out, and the ant would discover it one day when this master human being comes and smacks it on the head, and the ant says, gosh, here's an experiment, if it still survives, it would say, here's an experiment that I can't explain in my theory, so I better have postulated that there's what you call a negative space, a space outside my problem is we've never encountered, in centuries of doing experiments, we've never encountered any experiment which requires us to believe in a space outside of our space.
But at the same time, it's difficult for me to imagine there being no time.
Yeah, I know.
For how long was there no time?
But we learn that what is difficult to imagine may yet be true. It's difficult for you to imagine that the hydrogen atom has an electron going around a positron. That part is easy. Around a proton, that part is easy. But the electron doesn't actually move in orbits. Rather, its probability is smeared all around the core of the atom. You can't understand that. You can only see that from an equation. You can translate it into artist conceptions for people, but A, you would never have realized it if you didn't have equipment. B, if you didn't realize it, you could never understand the nature of atoms, and there are atoms, so quantum mechanics therefore is true whether we like it or not, whether we understand it or not, it's still true. Okay, and it's responsible for phenomena which are quantum, such as the fact that your phone emits microwaves and they go somewhere else and get absorbed. So here we face, for a physicist, it is a daily conflict. We are human beings. We like to party and dance and drink and everything else. But at some point in our profession, we have to realize that what we can imagine is not the point anymore. It's only what is true as verified by experiments, which is the point. All the rest of it we need to live. If we can't imagine, too bad. We have to learn to imagine. It's a fact of modern life, whether it was never a fact before the 19th century, because we never went into either the very micro world or into the world of things moving at the speed of light. So our imagination was pretty good. The people who really destroyed this, in some sense, are the Dutch. Are you Dutch? Yeah. The people who destroyed this are the Dutch, and the reason is that around the 18th century or the 19th century really, the Dutch became amazing I don't know what's the right word, not artisans. They became amazing at making machines. Okay? This was a civilizational jump, which obviously, you can try to trace from many things, cultural background, weather, climate, all the northern European countries had a lot of cold weather outside and a lot of time to sit indoors. They didn't have our monsoon, which rusts everything. They had presumably metals and glass, and of course they had a cultural history which came from the rest of Europe. as well as from other places. And then of course they were the Dutch, very hardworking and very serious about things, and they made lenses. And once they made lenses, all this lovely period of us being able to understand what was going on was lost. You look in a lens and you see things that you've never seen, but you have to believe them, because the next time you look in the lens, they're still there. You look in your telescope, the next time you look, those things are still there. Saturn has rings. Who knew? You know, or you can see, I don't know, you can see little microbes running around in your petri dish using these things. So that was the end of our innocence of being able to believe after we experience. Now we believe, but we have to let the instruments experience first. Nobody's ever seen an electron. You cannot see an electron.
But you can measure the effects of things you still cannot see.
Yes, absolutely. We do it all the time. Now, for example, if you stick your finger in an electric socket, you get a direct experience of electrons. Okay, lots of electrons. But that's such a lot of electrons. It's really a huge number. You might say, I want to get to know one electron better. What color is it? Everything has a color. Electron doesn't have a color. The electron is smaller than the wavelength of light, so it doesn't have a color. There's no point asking what color it is. Are there softer electrons and harder electrons? No, all electrons are absolutely identical. Again, you've never experienced any two objects that are absolutely identical in the fundamental sense, because in nature they don't exist. Even identical twins or identical leaves, they're so complex that you'll never be able, even identical cells aren't identical. It's when you get to an elementary particle, an electron, they're actually identical, which means the formulae by which we describe them, if we assume they are identical or non-identical, we get two completely different results, and the identical one is right. So it's beyond a shadow of doubt that every electron in the universe, in all respects, is completely identical to every other. We have to accept that. But it's very counterintuitive. Please.
Now, I don't know about this at all. It is something I heard, and I don't know that time is holographic.
Time is holographic? Wow. Okay. Yeah. I mean, if a PhD student came and told me that, I would say, yeah, maybe, but it's very, very speculative idea. It's something you heard correctly. I don't know how to explain time being holographic, because I don't know what it means, but I can tell you what it means that space is holographic. That we certainly do believe, or space-time is holographic in some way. The black hole, the concept of a black hole has changed our picture of space-time in the following way. Here's an object that's spherical, it has this horizon, but it behaves in all mathematical formulae as if there's nothing inside, as if everything that describes it is on the horizon. Okay? It's very strange because it's a three-dimensional ball. If it were just a shell, then we could go inside the shell, like an eggshell or a cricket ball, we could poke our fingers in and go inside, not like that. But it behaves as if, so its description seems to be sitting on its surface in the form of some bits of information. This is the result due to Hawking basically and Wittgenstein about 20 or 30 years ago. So this is now called the holographic principle. It says that objects which are solid can be described in terms of degrees of freedom living on their boundary completely. Okay? It's not something that can be explained in ordinary language, something that needs mathematics. However, if you have one of these identity cards with a little hologram on it, the same concept, that's not to do with gravity, that has to do with light. A hologram is a little three-dimensional picture, so if you move your head this way and that way, the picture moves as if it was real three-dimensional one. In fact, the first hologram was made of a chess piece, and you could actually go this way and see the side of the piece. But it's all on a plane. So it's encoding three-dimensional information on a two-dimensional thing, more powerful than a photograph. Photograph is just a photograph. But a hologram is a more clever way of encoding data on a plane. And gravity seems to have a holographic property, but it's something quite new and we still haven't understood it completely. And certainly not something that I would want to talk about in a talk at this level, because it's still very new and still very abstract.
One more question.
Please.
We relate time to light, as I believe, and as I understood it correctly, we can bend light by gravity. So in that sense, we can also bend time.
Yes, I think that's correct.
So,
And in fact, it's
explain
exactly
the cone.
Yeah, I think you should in fact think about the following. I mentioned in this figure I showed you that the presence of gravity actually bends space-time, and this picture. And this picture actually represents what you just said, because what light does is, in any space-time, it travels as straight as it can. The path of light is called a geodesic, and geodesic means that it just travels as straight as it can manage to travel. So when we say that a gravitating object bends light, what it's really doing is bending the space-time so that light curving around it thinks it's going straight. It's going straight with reference to that curved space-time. So the curvature of the space-time is really nothing more than the curvature of the light ray. And in fact, we now understand that the best way to understand curved space-time is to consider all possible curved light rays in that gravitational field. That builds up a nice picture of space-time.
Would it also explain the ice cone shape of time from the Big Bang?
I'm not sure it explains that.
I don't know, I'm just guessing.
Yeah, I'm not sure it explains that. And by the way, it's not absolutely necessary that there was a Big Bang. So the rival theory is the steady state theory, which is the universe was always there, it was only expanding and contracting, and what we see now as an expansion is just now, and later it will again contract, and then people go on, this was in the Vedas, this is the universe is cyclic, etc., etc. But all that is very fine, but finally there are like a dozen probes flying around out there taking data from the early universe, and what your theory says has to fit with what they're finding. And that's where the Big Bang theory is doing best.
I have a different question.
Please.
You said that mathematics is precision.
Yes.
So, is mathematics itself is precise?
Mathematics itself is precise, yes, I think so. I think as precise as it can be.
There are some notions that there can be anomalies.
Yeah, well, there are some problems with logic, which is basically the Gödel problem. But those arise in very special situations. But I think for the most part, mathematics, when mathematicians say 2 plus 2 is 4, they really don't leave any room for error in that. It's true in a very, very precise sense. And any basic mathematical system is set up on some axioms, and then the results follow logically from those. There's no wiggle room in that. That's the sense in which it's precise.
Yeah, but in the environment where the mathematics is trying to represent certain physical or phenomena in physical or wherever state, there is a perception that there is often bit loss. So when you put analog music, digital music, not all of it is encoded into.
In fact, I would say that's not an issue of mathematics, that's an issue of physics. And physics cannot be precise, but it can be as precise as possible. So your music, given an analog stream of music, you can make it as good as possible, and once you've reached that, then you stop trying, because you've done as much, you've extracted as much digital data as there was in your stream of music, and then you
So similarly, when mathematical equations represent phenomena which are happening in the world or in the universe,
Yes.
how accurate should they be believed to be?
Very good question. That's a really excellent question and a very difficult one. But what people would say is that luckily here we have two things. We have the equations and then we have the measurements and we can compare them. Okay? So we can always look for deviations. Once there's a deviation, a disagreement between experiment and theory, now we can try to say who is to blame. Is it the calculation or is it the measurement? Then we'll find there are errors in both. The calculation will have an error because your computer only keeps, let's say, your calculator only keeps 4 decimal places. So there'll be some digit lost every time you take a square root or do something. Your experiment is bound to have errors. I already told you, from unknown electrical currents or anything that's floating around. Then you try to quantify, put a bound on the error. The error is this % of the answer. You do that from the experiment, you do that from the theory. Now you see if they fit. If they fit, you are very happy. Then you try to reduce the error as much as possible. And the beautiful thing is we haven't hit any great limit yet. In the best theory we know, which is electrodynamics, we could actually calculate a particular frequency associated to a hydrogen atom to 8 decimal places. That calculation involves a lot of computation, but I think in modern times not a lot. It was already done about 20 or 30 years ago to 8 decimal places and measure it also to 8 decimal places. That is by systematically reducing the error as low as it will go. But there are systems where you can't reduce the error. And one of the most beautiful examples is when we look at the sky. So I told you about these probes which are probing signals of the early universe. You know why they can't reduce the error? Because you reduce an error by doing the experiment many times, but unfortunately we have only one sky. The actual problem in physics. It's called cosmic variance. It says you can't do better than a certain amount because there's only one sky. You can't have many skies and average over all skies to reduce your error. There's only one universe. We feel very sorry about that. So that's an example where there are unremovable errors.
In the case of speculative proposals, measurements can't be done because it's trying to explain something which hasn't yet been seen in evidence.
True.
So there it has to be taken as...
No, it's taken as a work in progress which will complete only when it leads to a prediction and the prediction is measured. Till that time, it's only a speculative theory and people can decide whether this kind of research is worth going on with or not. Part of the decision also has to do with money. Is it very expensive? So what I do is very cheap. I just need a salary and nothing much else, an office, laptop, you see. Because this is all, this is theoretical work. When it comes to an experiment, then the chips are really down. How much money do you want to spend to fund this collider that's in Geneva, which is funded by European nations, 1 or 2 of which are now actually bankrupt? Good question. In fact, can the nations fund the collider, or now the collider could perhaps bail out a few nations? It's that big a project. But there what happens is the project is always anchored in something very solidly established from the theoretical point of view, like a missing piece of a puzzle or an area where something has to be found. We don't know exactly what, but something will be found, and hopefully a few other things. So there you don't, invest untold money in something which is speculative. But in theory you can sort of go on speculating until either it dries up because we can't do anything with it, or it leads to an unexpected discovery that's measured, and that's the big moment. It's a slightly scary phase because you don't know if your 25 years worth of papers will eventually go in the dustbin or will go in the annals of your research. You really don't know at all. Can't be sure. Yeah, please.
I have 2 questions. One, that in modern times, the scientific research and the pursuit, does it not have any what you call cultural perception of each country? I mean, does it not have? Because hinting to the thing when you said of the circularity of time.
So, I mean, for you as an Indian scientist, I mean, does it not contradict in your own pursuit of understanding it? Because third thing, that while I was watching the video where the paper turns into ashes, I don't know, I just felt there was some sort of circularity to it.
Well, it's ashes turning to paper.
Sorry, ashes turning to paper, and you know, thinking.
Yeah, you know, that, of course, you know, well, you have asked many questions. One of the questions I will say is that, you know, finally we have to be guided by experiment. Experiment is what makes a theory right or wrong. And here I'll just do an experiment so that you can go away and say that you saw a physicist not just talk but also do an experiment. Here are my car keys, and I will drop it from this. Okay, my house keys. About 5 times as heavy as my car keys. I hold them at the same height, I drop them at the same time, they hit the ground together, even though one is 5 times heavier than the other. Aristotle thought it was self-evident that the heavier object fell faster, and it actually didn't occur to him to check. That's because the ancient Greeks actually didn't have the experimental method thought out in their heads. Though they were very smart in other things, this they didn't have. Let me give you a better example. Aristotle believed that men have more teeth than women. Now this one you would think he would check, no? He didn't check this. He believed that men have more teeth than women, and that's the end of it, but they don't. You know? So, you know, your culture may feel that it should be this way, but finally, you know, there's only one way to find out, which is to look at the teeth of sufficiently many men and women, make a chart and see what the chart is telling you, and the chart tells you, no, sorry, exactly the same. So this is where, you know, experiment trumps everything, culture, belief system, everything. There are still residual questions. For example, would my thoughts be guided in a different way if I was working in Marathi or Hindi or Sanskrit or Tamil? I don't know. Today the dominant language of science is English, but wasn't always so. In the 10th century it was Persian. 1,000 years before that it could have, 500 years before that could have been Sanskrit. So it keeps changing. But when it was Persian, that's when the Italians were using Persian textbooks to do science in Italy. Finally it didn't bother them that this is from Persia and it's a different religion and it's a different culture. You won't believe the textbook written in the 10th century in Persia on diseases and the concept of contagious diseases, I forget the guy's name, was used as a textbook in Rome till around the 17th century. That's a number of centuries for one textbook to be going. Of course, when the Italians got going, they trumped all this stuff completely. All the great revolutions in medicine and all other aspects of science took place in Europe around the time, Renaissance and so on. But before that, it was somewhere else. So there is cultural dominance of one region or another region, but it never helps to say, well, I should believe this because my culture predisposes me. Because finally, I should believe it only if it fits with experiment. And this is why, I actually get a little irritable when people say, in Vedic time, in Vedic scriptures, they talk about they talk about quantum mechanics. Was quantum mechanics known? So say, if they had quantum mechanics, they would surely have made mobile phones and laptops. Now, what was stopping them exactly? And people might answer, but they didn't have the technology. But you see, this is a wrong way to see science and technology. It's not that science comes from the mind and technology comes from the machine. As I told you with the Dutch example, science comes from technology and goes back to technology. It's the lens made by the Dutch lens makers, the watches made by the Dutch or Swiss watchmakers. Those enabled us to do science, understand new things, because of which the Dutch and Swiss watchmakers are actually out of business, because now you don't need to make those watches anymore. But they served their purpose for such a long time. They gave to science a way of understanding, which trumped everything else. Having said that, it's not that it doesn't bother one from time to time. It is a little bothersome. You never know, really, are we receiving instructions from Princeton and Harvard about what we should do? I don't know. I like to think not. They listen to us as much as we listen to them, so I don't feel it's a one-way thing of cultural flow or something. If it helps, I'll tell you a little anecdote. Some of my colleagues here at TIFR, before they had come here, were at Harvard, and they stumbled across a little piece of a theory which was called open membrane theory. It's related to strings. Open membrane has the abbreviation ohm. So they said we'll call it ohm theory, and they published their paper with the ohm symbol in the title. Needless to say, they then were contacted by lots of religious people from all over India wanting to know more details. That's another matter. But what they did do was for one day to force the whole world to download this ohm font onto their machine so that they could view the paper. So I was amused. I thought, good, everybody puts their culture into their work, but it's only the name of it. It didn't affect what's in the theory. Just the name. And just as the words quantum and mechanics is Greek and I don't know, maybe quantum is Latin or something, these words come from those cultures, so we can put our words in if we feel like. Everybody is free to do it. But finally, the words are only a very loose description, it's the ideas. Please.
Yeah, it's a totally different question, I think, but maybe it's more a personal question.
Yeah.
But since we're in an art gallery, how do you relate art to science?
I don't know, I'm very puzzled. I'm very fond of art, especially music, which I think I understand. Visual art, I don't think I'm terribly good at. I like it. And TIFR, where I work, as you might know, is the second best art gallery of modern art in all of India. Especially the progressive artist movement, Hussain onwards is represented in. Hussain lived in and worked in TIFR for 6 months in the 1960s, painting the mural commissioned by the Institute. And so we live in an environment of art which our founder, Homi Bhabha, actually very much believed in, and he was himself a consummate artist in many different ways. So obviously it's there, and obviously it feeds into some kind of spiritual feeling you get when you go into a place like that.
Scientist who's gone through an artist.
Okay. Well, we're happy to talk to you more and more at length. And my answer is a very simple: I don't know, but I'm interested to know more. There's a question from behind you.
What do you think about God and religion?
God and religion. Let's see. So, I'm just trying to remember an event from 10 years ago. So Stephen Hawking was here for a conference at our institute, and there was a press conference where, as an organizer, I was sitting on the stage with him, and he was asked, do you believe in God? And he gave a very nice answer, but I can't remember it. He said, I use God as a metaphor for the laws of nature. The point is, of course, a scientist will immediately poke holes in your question. Is it a well-defined question? What do you mean God? Which God do you mean? Do you mean a Hindu God, a Muslim God, a Christian God? Do you mean a God who intervenes, a God who doesn't do anything? Does your God hang around? Is your God male or female? Does he or she hang around here or just watch? Do they get involved, not get involved? You see, once you have to answer all those questions, you'll realize that there isn't actually, that word doesn't have one meaning. It has many meanings for different people. Now, if you come down to it all at the end and say, well, do you believe that human beings have spiritual feelings? Then I'll answer yes. I have no problem with that. Do I personally like a religion? Yes, I like Buddhism because I feel it places an emphasis on self-understanding and self-transformation, which suits me well. And it doesn't actually, it's not a religion that believes in God in the first place, and that, so it's simple for me. I don't have to ask all these questions. Should I want to stop other people believing in God? No. I I don't think one should interfere in what other people believe. Although Richard Dawkins keeps trying to do that, and I must say I find it very amusing. I'm sort of half on his side and half not.
Has to do what? What does he try to do?
Well, Richard Dawkins is this biologist, excellent biologist, I should say, in England, who sort of, who's sort of vigorous or aggressive atheist campaign. So he attacks religion on all fronts, and he makes very interesting points, which I think you cannot just throw away. He says, why is it that children are given a religion, they have to take the religion of their parents? Why can't you just let them decide if they want to be religious when they are old enough to understand what it means? Otherwise, you're just foisting a belief on them, which may not be correct, by the way. So, as you can imagine, this irritates a lot of people. So this keeps sort of going on and on and on. And that's it. They keep. It's a campaign he has this book called, what is it called? It's about the God Delusion, there you go. In which actually explains that belief in God is a delusion. But seems to me could also be a delusion to that you are there to explain to people how they should see the world. Okay, so I think
Just a final question. How do scientists look at that which is not science? I mean, how do you look at things which are not, or do you think anything which is not in the domain of science, or everything is?
No. I think definitely there are things that should not properly be in the domain of science, because I think all of, we might, for example, right now we don't understand nobody understands the human brain. It's the big open problem of this century or next century or whatever. Virtually nothing is understood. You can see what it looks like, and there are some segments, and it's made up of some things, and there are some neurons. But how it leads to anything that we do and all that, at some deep level, nobody understands. And maybe they will one day, but it's going to be so complex that it would not explain in a useful way what is love or anger or hate or sadness or grief or jealousy or anything. These are complex emotions which are part of us, and science will perhaps, in extreme cases, sometimes people have too much of one and they are, they need help because they have a mental problem. Science is needed. Psychiatry, in my view, actually helps, including medication, because of research that people have done. It doesn't always help, sometimes it helps. But fundamentally, there are things that I'm happy to. I don't sit and when I listen to a piece of music that I enjoy, I certainly wouldn't sit and try to dissect it. Though I could. I know enough about, the physics of music is not very complex. Something about harmonic analysis into frequencies. I could sit and dissect it. I don't do it because I don't think it's very interesting as physics. It's all sort of done, and it's very nice as music, so I'll leave it at that. So I think I don't certainly look down on things that are not science. But it is part of science in the sense each musical instrument is only vibrating according to some laws of physics. But what comes out is, if it's sublime, then it really cannot be just made by writing a program. There's something very, very sophisticated going on. Okay, so thank you all.
Thank you.
It's been a pleasure.